class, so section 2.2 talks about intercepts, symmetry, and graphing key equations. We've already talked about finding x and y intercepts a little bit, so I'm going to kind of skim over that section. So in order to find the x and y intercepts algebraically, you're going to use substitution. So to find the x-intercepts for any equation, you let y equal 0. And to find the y-intercepts, if any, you let x equal 0. So let's say I have the linear equation y equals negative 3x plus 2. And I want to find the x-intercept. What I'm going to do is I'm going to substitute in y equals 0. So here I'd have 0 equals negative 3x plus 2. I'd go ahead and isolate my x. I divide by negative 3. So I get 2/3 equals our x-intercept. Now, our x-intercept, typically, you want to write that as an ordered pair, right? 2/3 doesn't tell me much of anything. So we're going to write this as an ordered pair. And that is my x-intercept for the linear equation above. To find the y-intercept, let's let x equal 0. So I'm going to have y equals negative 3 times 0 plus 2. I get that y equals 2. And I have x is 0, y is 2, and this is my y-intercept. You could do the same thing for quadratics, cubics. You just have to make sure you need to factor first. And remember that they could have more than one x-intercept. The main thing I want to discuss in this section is symmetry. So there are 3 different types of symmetry. There's symmetry with respect to the x-axis and symmetry with respect to the y-axis. And then the next one we're going to talk about is symmetry with respect to the origin. So a graph is symmetric to the x-axis if every point x, y on the graph, like here we've got the point when x is 3, y is 4, also has the point x negative y on the graph. So if we look down here, we also have the point when x is 3, y is negative 4, okay? Meaning it's symmetric across the x-axis. You can kind of see that if I folded this graph in half across my x-axis, they would match up, right? They're symmetrical, okay? So the x-axis is my line of symmetry. A graph is symmetric to the y-axis if for every point x, y on the graph, we've got the point negative x, y. So here I have the point when x is 1, y is 1, and here I have the point when x is negative 1, y is 1 as well. Lastly, we've got symmetry with respect to the origin. Remember, origin is the center of our coordinate plane, the point 0, 0. So a graph is symmetric to the origin if for every point x, y on the graph, the point negative x, negative y is also on the graph. So for example, here we have this cubic equation. You could see that if I was to rotate my graph 180 degrees, it would look the exact same way. That's kind of one way for me to visualize it. So how can I prove if a graph is symmetric to the x-axis, y-axis, or the origin? So in order to test for symmetry, in order to see if something is symmetric to the x-axis, you replace y with negative y in the equation and simplify. What you're trying to do is find an equivalent equation. If you get an equivalent equation, then your graph or your equation is symmetric to the texted axis or origin. In order to test symmetry to the y-axis, you substitute in negative x and solve. And in order to test symmetry to the origin, you have to substitute in both negative x and negative y to solve. And then simplify. That will tell you if your graph is symmetric to the x-axis, y-axis, or origin. Quick note, not all graphs have any type of symmetry. Not all graphs have at least one of these symmetries. So something to keep in mind, symmetry. So let's test for symmetry. Oh my gosh, what happened? Okay, so I have x equals y squared is this first tiny equation right there. Okay, let's zoom in, or not. So I have x equals y squared. So the first thing I'm going to want to test is for x-axis symmetry. That means I replace y with negative y and see if I get the exact same equation. So I have x equals negative y squared. Well, that's going to give me x equals y squared. So the graph of x equals y squared has symmetry of the x-axis. Okay. Now let's take a look at the second example, also very tiny. We'll do that in orange. I have y equals 1 over x. So the first thing I'm going to do is test for x-axis symmetry. That means I put y with negative y. That gives me negative y equals 1x. So this is not equivalent, these two equations. So it's no x-axis symmetry. Let's check for y-axis symmetry. That's when I replace x with negative x. That would give me y equals negative 1 over x. These two are not equivalent, so there's no y-axis symmetry. Last but not least, let's test for symmetry of the origin. That means if I have x, I replace that with negative x, and y I replace with negative y. That would give me negative y equals negative 1/2 x. If I divide both sides by negative 1, I get y equals 1/2. So because both of these look the same, there is symmetry about the origin for this equation.